Look up on a clear day and the whole sky glows blue. But wait until evening and that same sun bleeds into orange and red. Here's the strange part. It's the exact same sunlight doing both. So what changes? The answer is hiding in the air itself. Start with the sunlight pouring onto Earth. It looks white or maybe pale yellow. But white light isn't one color, it's all the colors mixed together. Splitting it reveals the truth. Red, orange, yellow, green, blue, and violet, all riding along inside a single beam of ordinary sunshine. Here's the famous proof. Shine white light through a glass prism, and it fans out into a rainbow. Each color bends by a slightly different amount, so they separate and spread. That hidden spectrum was inside the light the whole time. The prism just pulls the colors apart so we can finally see them. Now every color is really a wave of light, and each has its own length. Red light has long, lazy, stretched-out waves. Blue and violet have short, tight, rapidly wiggling ones. That tiny difference in size, long waves versus short waves, turns out to be the secret to the entire color of the sky. Next, look at the air. It seems like empty nothing, but it's packed with molecules, mostly nitrogen and oxygen, trillions upon trillions of them in every breath. They're far too small to see. Yet these invisible specks are exactly what reach up and grab the sunlight as it streams down through the sky. When sunlight hits one of those tiny molecules, the molecule catches the light and flings it back out in all directions. Scientists call this scattering. Think of light pinballing off molecule after molecule, bouncing every which way across the sky instead of traveling in one straight, tidy line down to your eyes. But here's the twist that explains everything. Air molecules don't scatter all colors equally. Short waves, blue and violet, get scattered far more strongly than long red waves. In fact, blue light scatters several times more than red. The molecules grab the blue and throw it all across the sky. This selective scattering has a name, Rayleigh scattering, after the British physicist Lord Rayleigh, who worked it out in the 1870s. His math showed something striking. The scattering depends very steeply on wavelength. Halve the wavelength, and the scattering jumps roughly 16-fold. Short blue waves simply win by a landslide. So picture the daytime sky. Sunlight pours in, the air scatters its blue light in every direction, and that scattered blue comes at your eyes from all over the dome above you. Look anywhere away from the sun, and you're seeing blue light bouncing off the air. That glowing blue dome is scattered sunlight. But wait, violet waves are even shorter than blue, so shouldn't the sky be violet? 2 reasons it isn't. The sun sends out less violet to begin with, and our eyes are simply more sensitive to blue. Our color vision blends what's there and lands on that familiar sky blue instead. Need proof it's all about the air? Look at the moon. It has almost no atmosphere, no molecules to scatter the light. So even in broad daylight with the sun blazing overhead, the lunar sky stays pitch black. No air, no scattering, no blue. Earth's sky is blue because Earth has air. Now to the sunset. As the sun sinks toward the horizon, its light no longer comes straight down. Instead, it skims sideways through the atmosphere, traveling through hundreds of extra miles of air to reach you far more molecules than at noon. And all that extra air changes the color completely. Along that long path, the blue light gets scattered away again and again, until almost none is left heading toward you. What survives the journey is the light that resists scattering, the long waves. Orange and red push through the thick air and reach your eyes, while the blue has been stripped out along the way. That's why a setting sun glows orange and red, and why the clouds around it catch fire with color. You're seeing sunlight with its blue filtered out by a long slog through the atmosphere. Dawn does the same thing in reverse. which is why sunrises and sunsets share that same warm, fiery palette. Dust, smoke, and haze can deepen the show, scattering even more light and turning some sunsets a richer crimson. It's why skies can blaze after a wildfire or a volcanic eruption. The cleaner the air, the more it's the molecules themselves pure Rayleigh scattering, painting the colors above you. And the same physics colors the sea. Water scatters and absorbs light in its own way, scattering blue most and soaking up red so deep, clear ocean glows a similar blue. The next time the sky turns blue at noon and red at dusk, remember, it's one sunlight, sorted by the tiny molecules of air. So the blue sky and the red sunset aren't two different lights. They're the same sunlight, sorted by size as it travels through the air. If this sparked a little wonder, subscribe to The Curious Owl and keep looking up.